Performance profiling of load balancing algorithms in a cloud architecture. That's my project. So I'm Samir Salafu, and I was working with Nathan Turlington and Dr. Jeffrey Galloway on this. And so bioinformatics and cloud computing can be used to develop programs for running bioinformatics tools. The overall goal of our project is to implement a small computer cluster called the BioCloud that will handle and process the jobs done by bioinformatics tools. So this particular experiment focuses on sending requested jobs to separate servers. And so this allows for jobs to be processed faster. Instead of sending 5 jobs to just one server, we could spread it among any number of servers that we have. And this will make managing the BioCloud program less complicated for the user. For this program to work efficiently and swiftly, a load balancing algorithm needed to be developed. And so throughout the entire experiment, I used the FastQC job just as to keep it a base level for comparing the different load balancing algorithms that I created. And so FastQC is a quality control program that analyzes raw sequence data, outputting graphs summarizing the results. And so you could see an example of a FastQC output here on the right. And so it gives a rough overview of potential issues with the data for the users to further examine. FastQC was used as a standard control task to execute across the servers so that we could compare the performance to test for load balancing efficiency. And a performance profiler determined that FastQC was CPU intensive. And so that helped me decide which load balancing algorithms I wanted to create. And so the purpose of this experiment was to find the load balancing algorithm that will be the most effective for sending FastQC jobs to servers. And the hypothesis was that %CPU will be the most efficient algorithm because it takes constant snapshots of the CPU, %CPU. And so for the methodology, I use a total of 7 computers, all installed with Ubuntu version 20.04, so the 2020 version. And so one computer was the client, or in the case of the BioCloud program, it would be the user, and that computer had a graphical interface. And then 4 computers were servers. And so those 4 computers were the one that were handling all the jobs. And so all jobs were sent to one of the 4 servers. And then 2 computers were GlusterFS storage servers, and they were there to hold replicated volume information. So all 7 computers were connected through a shared replicated Gluster volume. And that was done just to make the test cases more efficient. We didn't have to, all the files were shared between computers. And so all the computers operated via Linux terminal commands, but most of the code was done through the Python coding language, with the exception of Docker being used for executing FastQC. So what that means is that all the FastQC processes and the output of the graph, that was done inside of a Docker container. And so that just makes it a bit easier to use. And so then the FastQC jobs were sent through sockets. And so that's why the Python coding language was used, because Python already has socket methods in place and we wanted to utilize those. And then we also created a MySQL database with 2 tables. And so one table held static information about the 4 server computers. And then there's a second table that held the job count for each server. And so there's a total of 4 Python scripts used throughout this experiment. The first one, functions.py, contained methods that requested dynamic information from one of the 4 servers. And so this could be disk space, network, 1-minute system load average, any of that information. And then that Python script also contained methods that queried or changed database information. So one of the load balancing algorithms needed to change the job count. And so the method to do that was in the functions.py. And then another script was poll.cli.py. And so both functions and the poll.cli, these were operated on the client server. And so the second Python script contained the load balancing algorithms, as well as the algorithm for the test case. And so you could see that on the right here. And so this is a pseudocode of how we manage the test cases. And then there were two other Python scripts, and these were run on the 4 server computers. And so one ran in the Linux background, and this contained all of the things that like a regular socket does. And so like it could receive and send information, while the second socket server Python script ran in the foreground. And so that one captured data such as start and end timestamps or the current free RAM if the incoming data included the FASTQC in the text that was given. And so the 4 load balancing algorithms that were created for this experiment, so they were all dynamic. And so that meant that I pulled a resource before sending a job to one of the servers. And then, as I said before, all of the server information, part of it was stored in the database, that was the static information, but some of it is more dynamic, like free RAM and 1 minute system average. So there was a nested list that contained all the information, both static and dynamic. And so the load balancing algorithms worked by updating a specific resource. And so here you could see the specific resource that each load balancing algorithm looked at and to the most current information in the nested list. And then it identified which server contained the minimum of that resource. And then it sent the job to that server. So system load looked at Linux's uptime, specifically the 1 minute system load average. Percent CPU looked at the top command and like it looked at the percent CPU number. And then free RAM worked a little bit differently because all the nodes had different RAM space. So it looked at the free, like the available RAM, and then it calculated the percentage of free RAM out of the total RAM out of all 4 nodes. And then it just sent the job to the server with the least percentage of free RAM, or sorry, the one that with the most available free RAM. And then the last load balancing algorithm was round robin. And so that was the one that looked in the database and looked at the table that contained the job count. And so it just sent the job to the server with the least amount of jobs. And so here are the results of our experiment. And so we had a total of 7 test cases. And so there was 4, 8, 16, 24, 32, 40, and then 48 jobs in total. And so that was for like each of the test cases. And each of those test cases were ran 10 times. And so in graph 1, you could see that all load balancing algorithms were given the same total number of jobs. And so the only difference in this graph are the time taken to complete the jobs. So most of them follow a linear type function with the exception of free RAM. It's the yellow one that's going all over the place. And so this may have been caused by the uneven distribution of servers when using the free RAM algorithm. All 4 servers were used in the round robin, system load, and percent CPU load balancing algorithm, but free RAM only used servers 2, 3, and 4. This is because server 1 has the least amount of total RAM and only 2 CPU cores, so it can't handle as many FASTQC jobs as the other ones. It was calculated that server 1 can only handle a maximum of 30 jobs, while the other servers can handle a total of 50. So for the RAM algorithm, test cases 1, 2, and 7, all jobs were sent to one server. And so that can be seen where in test case 1 and 2, the time taken was significantly less than the test case 3. And even test case 7, it is significantly less than the time taken to complete test case 5. And so then when we look at graph 2, the free RAM load balancing algorithm, once again, has the highest times in system load averages. And so as before, that's because the RAM load balancing algorithm loads up one server with a lot of jobs before moving on to the next one. And so that means that that one server gets overloaded, which means it increases the system load, and then it also takes a long time to complete the jobs. On the other hand, round robin over here, which follows still a fairly linear path, it distributes the jobs evenly, but not all servers are equally weighted. So servers 1 and 3 have 2 CPU cores, while servers 2 and 4 have 4. So that means that systems 1 and 3's system load was overloaded much faster than the others. And so the time taken to complete the jobs is higher than these last two algorithms, percent CPU and system load, because these last two algorithms take into account the CPU percentage or the system load average. And so since both, like I said, since both of these take into account, they have significantly less system load and they take less time, but percent CPU manages to look at CPU a bit better. So percent CPU, it changes almost every second, while system load, it's a 1 minute system load average. So it doesn't actually change every 1 minute. It's actually about every like 10 to 15 seconds. But even then, the percent CPU's changing 1 second. That means it's much faster, and it's able to like take a look at the how well each server is handling their jobs much better than the system load. And so that's why the percent CPU has the least amount of system load for all test cases. And then in the third graph, the free RAM load balancing algorithm has the largest free RAM. And so that's because the free RAM was averaged among all servers, despite them having different total RAM. And so that meant that the data is a bit skewed, but since this was done to all the load balancing algorithms, I can still compare them fairly equally, with the exception of this free RAM load balancing algorithm, because as I said before, it does not contain any data from server one, and server one does have the least amount of free RAM. So that is most likely why the free RAM algorithm is so much larger than the others. And so then based on our results, it was concluded that percent CPU is the most efficient load balancing algorithm. It's because it manages to complete the same number of jobs in the least amount of time. As we can see here, percent CPU is the lowest in this graph, and it also has the least system load for basically all of the test cases. And while it isn't exactly the best on the free RAM isn't exactly a good indicator for the FastQC job, because as you see, the next bullet point is that FastQC is not RAM heavy. And so like I said, for like test cases 1, 2, and 7, it sent all of the jobs to server 2. So that just means that FastQC doesn't really impact RAM that much. And so the RAM load balancing algorithm isn't really a good algorithm to use for this FastQC job. But it was determined that FastQC is CPU intensive. And so as you can see, especially with this system load graph, all of the load balancing algorithms reach a system load of 5, even though the maximum core count was 4. So that means at least all of the load balancing algorithms, all servers were overloaded at some point. So the FastQC job is CPU intensive. And so problems do arise when too many jobs are run on one server. The system load becomes very high, and then all the Docker containers are not stopped and removed as they're supposed to. And then when the containers remain running, they require disk space, and eventually this becomes full and jobs cannot be completed. So that's why it's very important that we pick a very efficient load balancing algorithm so that all jobs manage to be completed. And so I created a polynomial regression equations for all of the load balancing algorithms to kind of compare them. And so whenever an equation has like a power of x to the fourth or even x to the fifth in some case, that means that like the load balancing algorithm struggled to follow a trend line, and that load balancing algorithm isn't exactly the most efficient. So in the case of graph table 2 lines up with graph 2, the free RAM has a power of x to the fifth. And if we look here, it's a bit random. It doesn't exactly follow a trend line. So that means that it's hard to like estimate the time that it will take to complete jobs. And so this free RAM load balancing algorithm is not that good of an algorithm for FastQC. Instead, whenever we have like x squared or even x cubed as well, that means that the algorithm is more efficient. So percent CPU, the algorithm that we deemed the most efficient algorithm, has x squared for all graphs. And so this can be seen whenever we look at the graphs. This is fairly linear, and this one curves a little bit, and that's why it's quadratic, and this one is fairly linear as well. And so the polynomial regression equations support the hypothesis of percent CPU being the most efficient. So in conclusion, 4 load balancing algorithms were created and tested in this experiment using the FastQC bioinformatics job. CPU was the most efficient load balancing algorithm, and that was once again because it had the least amount of time to complete jobs and it had the lowest system load averages. In the future, more data will be generated using more bioinformatics tools in order to create a dynamic biocloud platform. And so the bioinformatics tools may be of different types. So FastQC was CPU intensive, but another tool may be RAM heavy or disk heavy or whatever. So a different load balancing algorithm may be more efficient. And so then we also hope to work on load consolidation algorithms to see which kind of algorithms are more effective for each bioinformatics tool. So in that experiment would be comparing load balancer versus load consolidation. Here are my references. Thank you so much for your time. Do you have any questions?